Today I'm going to talk about LeetCode question number 743, network delay time. So given a network of n nodes labeled from 1 to n, you're also given times, a list of travel times as directed edges, where in times I, u, v, w, where u is the source node, v is the target node, and w is the time it takes for a signal to travel from source to target. We'll send a signal from a given node k. Return the minimum time it takes for all the n nodes to receive the signal. If it is impossible for all the n nodes to receive the signal, return -1. Okay, so in this example, the output is 2 because it takes 2 time units, so 1, 2, in order to have the signal reach all nodes. This guy takes 1, but we need a minimum 2 for it to reach all nodes. Okay, so this is a good case of Dijkstra's algorithm. Okay, where Dijkstra's algorithm basically computes the shortest time it takes to get to each node starting from a source node here. Okay, and how is Dijkstra's algorithm going to work in our code? So basically, how it's going to work is we're going to have we're basically going to turn this into an adjacency list. First of all, adjacency list where if it has, a node, it lists out all its children. It's going to be a dictionary here. So if you have a node, it's going to, as an array, list out all its children, like, etc. Okay. And actually, in this adjacency list, we're not just going to list out the nodes its neighbors to, we're going to list out the node its neighbor to along with its weight. I'll do a more concrete example. So for like 2 here, it's going to have an array where it's going to be like 1, 1, okay, and then 1, 3, okay, where 1 is the first one here is the weight here, and the second element in this tuple is the node itself. Okay, so we're going to have an adjacency list for that. Okay, we're also going to keep track of weights, and this is going to also be a dictionary, and it's going to keep track of, starting from the source node, how long is it going to take to get to each node. So for like 2, obviously it's going to be 0. For 3, what we're going to initialize this to is actually infinity. And during Dijkstra's algorithm, which is a kind of a breadth first search here, we're going to make this smaller eventually to the smallest time it will take to reach to 3 from the source node. Okay, and similarly 1, infinity, etc. Okay. So that's some Dijkstra preamble, just setting things up, and we're also going to have a visited set here. Okay, it's going to keep track of the nodes we visited during Dijkstra's algorithm. Okay, now let's get into the meat of it. So what are we actually going to do in Dijkstra's algorithm? Well, we're going to have a heap, a min heap to be specific. Okay, why do we want a min heap? Actually, I'll draw it like this. Okay, so why do we want a min heap? Because for Dijkstra's algorithm, it basically says, okay, starting from 2, how long can it take to get to 1 and 3? Okay, initially you're going to have 0, 2. Okay, in here, the 0 represents how long it's going to take to get to 2, and 2 represents the node itself. So obviously 2 is the source node. It's going to take 0 time units to get to 2 because we're already there. Okay, now for each of 2's children, how long is it going to take to get there? Okay, so for 1, it's going to take 1 time units to get there. Okay, first we're going to pop this, okay, and then 2, 3 is going to take 3 units of time to get there. Okay, great. And now what we're going to do is, now we're going to go through the next iteration of Dijkstra's algorithm, or breadth-first search. So now we pop from the min heap the node with the smallest weight. These two are tied, so let's just pop this guy here, okay? And now, starting from this node 3, how long is it going to take to get to 4? Okay, from this node 3, how long is it going to take to 4? It's going to be actually 2, 4. Why 2? Why not 1? Well, we want the total time it will take to get from 2 to 4, and that's 1, 2, okay? So we have to add, this guy here to this weight here, okay? So that's what we have to do. And meanwhile, I forgot, in the weights, in the weights dictionary, so we have like 2, 0 here, and then 1. So in this first iteration here, we had like 1, 1, and 1, 3. So before it was infinity, then we get the min of what we calculated, here. So it'll be 1, and 3 will now be, which is originally infinity, now is 1, okay? So now we have a 4 here, and then 4, it was originally infinity, then we take the min of the time it'll take to wait till it to get to 4, which is now 2, okay? Next iteration, we're going to keep doing this till min heap is empty. Next iteration, what do we pop next? Well, we pop the node with the smallest weight, and a min heap will help us do that. So it'll be 1, 1 next. Okay, now explore its children. It turns out it doesn't have any children, okay? So we just leave it alone there. And meanwhile, we're putting all these in visited. So we visited 2, we visited 1, we visited 3, and then we visited 1. Okay, and now we're going to visit 4. Now we visited 4, and 4 doesn't have any children, so it's a 4. So 4 doesn't have any children. Okay, we'll leave it at that. And what's the point of this visited? Well, if we have a cycle, like if we had a 5 here and it goes to 3 here, then obviously with 4, we'll visit the 5. Okay, calculate the time we'll get there. Let's say this is 2. Okay, we calculated 4 to take 2 time units to get there. Then 2 plus 2 is 4, so it'll take 4 units to get from 2 to 5. Okay, in the smallest path. So yeah, and then we visit 5's children, but we already visited 3, and we don't want to keep visiting 3's children over and over again. So that's why if something is not invisited, we visit it, we explore it and its children. But if it isn't visited, then we skip over it. Okay. What if we had like 2 go to 5 like this, and it takes, I don't know, 10. Okay. Dijkstra's algorithm will help with that, because let's say, we start over with like 0, 2, okay, and visit, and in our weights here, then 0, 2, and its children are 10, 5, and 1, 3, okay. Then our weights here are 5, and then 10, and then, which was originally infinity, and then 3, and 1, okay. So we do that, and then we calculate all the way to 4, and then from 4 we get to 5 again, okay. But for 5 it takes 2, 3, 4 units to get here, and our weights we have 10 units, okay. Then we take the minimum, so this will get replaced with 4, okay. And the runtime of this is O of E log V. And why is that? Well, in a graph, the number of edges that we can have is V squared. So if you have like 3 edges here, the maximum edges is like that, okay? Where it can be like bidirectional here. And then so we can have maximum V squared in our heap here, okay? We can have like in our heap like 10, 5, and then I don't know, 4, 5, but in our min heap we'll pick 4 or 5 every time. So in our min heap we can have maximum V squared, okay? And we're exploring each edge in Dijkstra's algorithm here, okay? So it'll be O of E log V squared, but in the case of logs, you can take out this exponent here and add it in the front, but we don't ignore constants in big O notation, so the O of E log V. Okay, now to code it up, so what I want is a weights graph here. For I in range 1 n plus 1, we're going to assign weights, or actually first, you want to take care of condition. If I is equal to k, the source node, then weight I will equal to 0, else weight I will equal to infinity, okay? And now what do we want? We want our adjacency list here, okay? So we're going to go through each of these edges here. So for source, destination, and weight in times, okay? If source not in adjacency list, then adjacency list, we're going to initialize it first to an empty array. Adjacency list source is equal to first an empty array, okay? And then after that, no matter what we do, whether it exists or not, we want to source.end. We want to append now is our weight and our destination here, okay? So we have that, and then we want our visited set and our heap. I'm going to turn this into a heap. Heap. Okay, great. And then our first thing in our heap will be q.heap push will be our source node. Okay. Okay, so the preamble is done there. So now let's get to the meat of Dijkstra's algorithm. So while the length of heap is not equal to 0, what we're going to do is pop. So weight node is going to be equal to heap q dot heap pop for the heap, okay? And for the heap, we're guaranteed to pop the smallest thing every time, smallest weight. That's how we're storing in here by weight and then node, so we'll always pop the smallest weight. Okay. And then if node in visited, then continue. Or if node not in adjacency list, node like doesn't have any edges there, then if a node doesn't have any children, then continue also. And if a node doesn't have any children, then if a node doesn't have any edges coming out of it, then obviously it doesn't have any. If a node doesn't have any children, it doesn't have any edges coming out of it, so there won't be any times already here. Okay. So now what we want to do is get the children of node. Okay, and then iterate through each children. Oh, also what we want to do is mark this node as visited. Visited.add node. Okay, so in case we have a cycle, we don't visit this node again and keep iterating over its children over and over again. Okay, so we have children. So for child in children, I'll explore children here. If child not in visited, then basically what we want to do is update the weights here for that child. So weights child, we go to the min of itself. For child and children, oh, I forgot. For and so for weight child and children, okay. Don't really feel safely doing this. So for child and children, and we gotta remember child is a tuple with weight and node. Okay. So for child, not if child 1, okay, not in visited, then weight of child at that node. Okay, remember I to position this tuple is the node itself. Close min. Weight child 1 and it's made of weight child 1 and child 0 plus weight up here. Okay. And we want to push this onto RP. So child 0 and that's a tuple. Yeah, okay. Great, that's pretty much it for declist algorithm. Now we want to do is, get to a question here. What's the minimum time it takes for all end nodes to be reached? So I'm going to iterate through weights here. So for node val in weights, my result here, and I'll initialize it to -infinity, because we want the biggest value in weights right now. Okay, like this takes 1 second, this takes 2 seconds, we want 2 seconds. If val is equal to, still equal to infinity, then return -1, because that means rename it there. So wait, so if it still equals infinity, that means that node was not reachable at all. So return -1, else result is equal to max of itself and wait. Okay, and then return result. Let me try running the code here. Okay, push up. Oh, wait, dot. Wait, that's how you would read over dictionary. I missed that. Okay, and I'll submit. Okay, great. Thanks for watching.